next talk is by Andreas Glatz, and there's the title there. So.
Yeah, go ahead. Okay, thank you. And first, let me also start thanking the organizers for giving me the opportunity to talk at this nice conference in this beautiful location. I will talk a little bit about Ginzburg-Landau simulations, large-scale simulations, and in particular, I want to address one particular problem of a nanoscale superconducting slab where you apply current and magnetic field in parallel. And before I go to this, I will show you a little bit our motivation, why we, as you heard yesterday, there are already many groups who work with Ginzburg-Landau simulations, but we try to go to really large length scales to address some problems which are beyond the reach of current technologies. So what is our motivation to do this? So basically we want to simulate large systems where we have a lot of vortices included in the superconductor which interact, and they can interact by splitting, for example, by reconnection. And you can only address these problems when you do large-scale simulations where you have hundreds or thousands of vortices in the system which you want to study. Then if you say, okay, I could do this with some simplifications like Langevin dynamics where you model only vortex line, or XY simulations where you forget about the amplitude of your oddometer and only study phase information, you cannot address these problems. So you really need to at least implement Ginzburg-Landau equations, and this gives you a way to model basically mesoscopic systems. And I mean, our motivation to do that is basically we want to build a basically tool to predict superconducting pinning landscapes inside superconductors to increase the critical current and get some optimum. This is what we call a robust optimum. So we basically want to optimize the pinning landscape such that we have the highest possible critical current. Or in terms of catchword, you would say this is pinning by design. And this is a bigger project which we are doing at Argonne National Lab, which was funded 2 years ago by the Department of Energies, and we take or we use the largest available computing facilities which we have available. So this is here the list of the current fastest computers, and we have at the moment the 5th fastest, and we're actually utilizing these machines right now to address these problems. So in particular, we are working on 2 different kinds of approaches to solve Ginzburg-Landau equations. One is to model basically superconductors and pinning centers on a regular rectangular grid. So you can imagine 2 or 3 dimensional superconductors, and you put a regular mesh in it. And we use for this approach modern architectures like GPUs or Intel mic architectures, or we also model more complex structures where pinning centers have various shapes, and we model this by some unstructured grids, which are then modeled also to run on these big machines here, because this really requires a lot of computational power. So this is just the project which we're working on. If you want to look up more information, you can also see our website. So this is basically internal collaboration at Argonne National Lab, and we work together with the computer science department here to develop these novel codes. And since this is a multi-component or multi-band conference, all these tools which we are developing are more or less easy to adapt also to multi-bands or even multi-components. But here we'll address mostly the problem of a single component. You could, or maybe you can say the pinning centers are different components, but I'll just demonstrate by the example of this slab where you apply pair fields and current, what we can do with that. So I will briefly introduce how our solvers work and how we solve these equations. I will show you the experimental motivation, why we study this particular problem. This is not related to the prediction of critical currents, but this is basically the other way around. We have an experimental result and we want to understand why we have this reentrance behavior which is observed in these experiments. Then I'll show you how we realize this in a simulation and show you our results. And a very interesting part of this work is to really understand what is going on in these superconductors and why we see this reentrance behavior. We need a very sophisticated analysis of the order parameter information and a very sophisticated vortex detection algorithm. So this is just introduction, most of you probably know. So we solve the Ginzburg-Landau equations. This is basically the Ginzburg-Landau equation and the Maxwell equation. These are the two equations in dimensionless form. We model inclusions here by modulating basically the critical temperature inside pinning centers. This is given by this epsilon of r. Then the critical current has to be calculated self-consistently so we can apply a constant current to our sample. And
Andreas, excuse me please, but zeta of RNT, these are Langevin forces, or what is this?
This is thermal noise. So we also have, I mean, since we are working at some given critical temperature, this determines basically the amplitude of some thermal noise.
Just a question. So for the static Ginzburg-Landau, we can show that this is an effective theory of BCS.
Mm-hmm.
For Mediasbeck theory, you do not end up with an effective time-dependent Ginzburg-Landau. So is this what is it?
This is time dependency.
But this is approximated in some sense.
Well, I mean, if you are in a steady state, then the time dependence gives you the real physics in the system. If you want to study relaxation processes, probably this equation will not give you the real physical relaxation mechanism.
Sorry, one question. So
Yeah.
this noise is, how do you set the noise? It is consistent with fluctuation dissipation theorem or something like that?
Basically, I mean, you can, yes, but you can calculate basically what is the amplitude by the given critical temperature of the material. So this is determined by the material which you study. So, and in this parameter here, you just fix the ratio between the temperature at which you study your superconductor and the critical temperature, but the absolute value of the critical temperature is encoded in the amplitude of the noise. The same equations, by the way, can be used in a slightly different form also to describe cold atoms, which we also do. And there also the noise term is very important to describe dissipations if you study, for example, cold Fermi gases. And then also the critical temperature of these systems, which are a few nanokelvins, enter this noise term. But they're really important in this case as well. So here we focus, since these systems are usually very thin nanometer thick samples, we study on the case of very large penetration lengths or the large kappa limit, and we basically apply a magnetic field in basically arbitrary directions. This here is written for perpendicular direction, but in our case we study the field paired to the current in the x direction. So in this case, you can also simplify the expression for the supercurrent, and basically you can do a small transformation of your scalar potential here mu by addressing the external current which you apply to the system. The reason why you do this linear rescaling of the scalar potential is that you basically create scalar potential which is suitable for calculating it easily in a periodic boundary condition situations. Then we also simplify the order parameter a little bit, or we basically do some phase shift here by applying some phase factor here, which is related to the integral of the voltage of the system. And this way allows us to prescribe complex boundary conditions to the system, which otherwise would be almost impossible to address. So then we apply a constant current here, and every time step you have self-consistency to solve the equation for the current, and you need to adjust this parameter k here. Again, this is the integral of the voltage of the system in order to stabilize a fixed external current. You could also imagine you want to stabilize the voltage, which is given here by the time derivative of this parameter k, and then you just invert this equation and you can stabilize the voltage and find out what would be the current related to this voltage. So for the scalar potential, you also need to solve the Poisson equation. Because of the complex boundary structure which we have typically, we have to do this also in a little bit more complicated way than you might think is possible. So we basically introduce a virtual time scale here, which also describes a super relaxation of the scalar potential towards the static solution given the order parameter. Because if you look at these equations, you might think you can solve these by some spectral method, so use a Fourier transform and solve it, but unfortunately this is here not always possible. But anyway, this method here is rather efficient in our scheme as well. For the time discretization, we use a fully implicit method called the Krenk-Nicholson scheme. And this gives you a linearized equation system which we solve. I won't go into the details of the spatial discretization here, but for the time discretization, you need to solve the implicit system, which we linearize, and then have to invert this linear equation system. Just a word about boundary conditions here. We typically have two situations. One is when you have surfaces where you have no supercurrent perpendicular to the surface, or you have periodic boundaries. But this is not always possible for a given magnetic vector potential, so you have to prescribe something called quasi-periodic boundary conditions, where at the boundary the phase of your order parameter has to make a jump, which is related to the applied magnetic field. The same happens actually also if you have a finite current applied, then you have additional phase factors at the boundaries if you want to have a periodic system. As for the linearized equation system, we want to implement this on parallel machines and want to scale it to 10,000s of processes. So you need to use very difficult, or not difficult, but sophisticated schemes. And in particular for the regular mesh, which we implement mostly on the graphic cards, we use something called the Jacobi iteration, where you just decompose this linearized matrix and invert it iteratively. And this method is very efficient. So basically you need to iterate your solution every time step about only 4 to 5 times to reach an accuracy of 10 to the 96. So here's just an example how we model inclusions. So as I mentioned, we model inclusions by modulation of the critical temperature, and we study also thin films which are perforated here in this example. So you have a superconductor around some normal inclusions here, and then you can apply a magnetic field which is perpendicular and solve the Ginsburg-Landau equations, and you see here a state where you have vortices in between these inclusions. But for example, in this picture here, this is the amplitude of the order parameter. You won't see how many vortices are inside these inclusions. I will address this in the second part of the talk. So now I will finally come to the experiment which we were interested in to study. So in a group of Zili Zhao, they made an experiment, again, where you apply a current and magnetic field in parallel to a molybdenum germanium sample. And the parameters of these samples are given here. So the thickness of this slab is about 100 nanometers. When you consider the zero temperature coherence length of roughly 6 nanometers, this corresponds to a thickness of 16 zero temperature coherence lengths. The critical temperatures is about 6 Kelvin here, and penetration is 400 nanometers. So you see that the ratio of these two gives you or validates our large lambda approximation here. And this is the observation. So you apply the current in this way, which is constant, and then you increase the magnetic field here. And what you observe is quite interesting. That first, as you would expect, the resistance goes up, but then suddenly there's a sharp drop at low temperatures, where basically you recover superconductivity before your sample becomes completely resistive and might even become normal here at higher temperatures where the critical field is lowered. So at this point, there were no real understanding of this phenomenon here. So we tried to find a way to simulate this sample here. And this is our realization basically of the sample. We used a regular grid. Our mesh size is about half of the zero temperature coherence length. We use 32 grid points in the z direction, which is the thickness. And in x direction, it's a very long sample, and we have a periodic boundary condition in x direction. Again, we also need inclusions here, which are modeled by TC modulation. The current is also applied in x direction. And this gives you about 2 to 5 million grid points, which we are simulating for this particular sample. And as you see, 32 times this half psi zero basically gives you the 16 coherence length, which the experimental system actually has. So we basically simulate more or less exactly the system which is described in the experiment. So for these systems, we need to relax the order parameter quite a long time. So we basically solve the equation for about 25 million time steps. And we increase the field during this time at 100 steps. So this is here isosurface movie of the order parameter. In this case, you have a clean sample, no inclusions, and you just see here the increasing field in x direction. So this should be Vx here. And you see just the number of vortices increases, but the vortex lattice is more or less stable because there's no effective Lorentz force on these vortices since they are prior to the field. Only if you come to very large field values where thermal fluctuations might move your vortex a little bit out of this alignment, the Lorentz force might be big enough to destroy the superconductor, which you see at the end, when basically the whole superconductor starts to break down. So then we tried to understand, so this simulation basically cannot explain the experiment. So a clean sample wouldn't produce this effect. So then we tried to add more inclusions here. But if you add too many, then basically all these inclusions bend your vortex lattice in such a way that you always have a Lorentz force and then you always have dissipation. So basically at HC1 you get C dissipation, and basically you will never get rid of it. There's no re-entrance and you always be in a resistive state. So then we needed some mechanism to bend vortices a little bit so we have an effective Lorentz force in it. So we added only a few of them. And then suddenly we saw something very interesting. So now we increase the magnetic field, and at intermediate values you actually see some motion, and then if you further increase the field, you see actually that the additional vortices basically stabilize this motion again, and basically you are back into the dissipational state. So if you look at the time-resolved voltage here, so the blue curve is first the magnetic field. So over time here, this goes up to 10 to 6 Ginzburg-Landau time. So if you estimate the Ginzburg-Landau time as 10 to minus 11 seconds, this would be a total simulation time of a few microseconds. So you increase the magnetic field up to a third of the zero, the critical magnetic field at zero temperature, without current, of course. Then you see for single realization of impurities that you have some intermediate regions where you see some finite dissipative state. So this is again for one disorder configuration here. And now we wanted to understand what is actually happening in these regions. So we chose a particular magnetic field value, which is here 0.12, and looked what is going on in this region. So this is here this magnetic field value 0.12, and what you see is actually something very interesting. You have some kind of helical motion of vortices that vortex lines bend, go to the surface, and then they travel around the boundaries of the system. And this is a very periodic motion, which you see also in the time dependence of the voltage. And as you see, this is a perfectly periodic system. So here, the voltage versus time at this particular fixed magnetic field here. And as you see, if you would average these voltage values over some time, because this is what you would measure in an experiment, you get a finite voltage. While if you have a larger field, again, you would recover a zero dissipation state. So this is unfortunately not the complete result. I only had time to average a few sample realizations. But here you see magnetic field versus voltage in this case, not resistivity, and you actually see that we can find this effect of dissipation full state at intermediate field values, and then at a certain field value the vortex lines stabilize again these helical motions, and your resistance or voltage in this case goes down before the system goes into the resistive state. So now you saw mostly isosurfaces of the order parameter, but in order to understand what is really happening in these systems, it is very useful to develop a technology to really, to figure out how vortex lines are actually moving and what is happening when, for example, one vortex line crosses other vortex lines. So again, as I mentioned, this amplitude visualization or estimation of vortex location is rather inexact. You cannot actually see what is going inside inclusions. You still have a residual order parameter in there due to proximity, but in these simple isosurfaces, you cannot really see what's happening inside. So you lose all the fine details, especially inside the inclusions, and additionally, you cannot describe the chirality or vorticity of the vortices this way. So you need to do something else. So what we are doing actually is around each mesh of our cell, of our simulation grid, we need to do contour integrals of the gradient of the phase to find out what is the phase jump if we go around one phase of the mesh cell. So this can be either regular or unstructured grid, and this way you find trivially also the chirality, so if a vortex goes in or out through the surface, we find the vorticity, and this calculation is also highly parallelizable, so this is very important for us to do this efficiently, because you can imagine for a three-dimensional sample, we have for each grid point of the grid, you need to do 3 contour integrals to capture all the 3 phases, and then you can interpolate the puncture point of vortices for each of the mesh cell, and this way track vortices through the sample. So an additional problem is if you look at the phase information of some, this is some random vortex data in 2 dimensions. Again, these are contour lines. They don't give you too much information, but if you look at the phase values, you see at some point when the field becomes very large or you apply a high current, then your phase lines, these are here between minus pi and pi, become very dense, and at some point you might not be able anymore to actually calculate these contour integrals, and in order to overcome this you also need to gauge transform your field order parameter back, and then you can actually extract something like this here where you do a simple line integral and extract all the vortex information. Just to show you what we can do in a system where you have 1 billion degrees of freedom, we could track more than 1,200 vortex lines inside the systems. And this you have to do every time step, so you can imagine this is a very time-consuming task, but you can do it. And just to show you how long it takes, if you would do this in MATLAB, it takes more than 30 minutes to create this vortex figure here. If you do it on a GPU, you can do it in less than a second. So here just a comparison again between isosurfaces, so you don't see much details, but if you do the vortex detection, you actually can see the vortex lines, even what is happening inside, till the point where your order parameter amplitude is below some certain threshold. So this here is just an example of a single inclusion in the center. And then you see these are just noise phenomena because we cannot resolve anything anymore, but in the beginning you see a lot of relaxation going on. This should also move. This is just a cylindrical defect, and you see here, for example, that vortex, anti-vortex line here, they're also colored differently with their chirality. They split due to fluctuations, and if you increase the field or the current, they separate and leave your inclusion. And depending on the size, you see there's a lot of noise going on because the amplitude of your order parameter is too small to detect anything. But you see how useful this can be. Here for our sample of parallel fields, you actually can see how vortices are moving, how they disconnect when they touch and then reconnect again. So you actually can see if they touch, they do double touches, so they split, reconnect, and then they split in a different way. This is again the periodic state here, just one more last movie. So if you have a strong higher field, you see how the system basically stops. And this is the re-entrance effect of the superconductivity here. Okay, one last word about what we can do next is we can also study some topological properties of vortex lines. Namely, we can study twist and wave. The question would be, how can you define these two properties for a single line? Well, you have to look at the phase again. If you look around, here's the puncture point of a vortex. If you go around, your phase changes from minus pi to pi at some point. And this line where it jumps, you can define as a direction, as for example in a DNA where you have a band. When you twist it, you can define the twist, but for a vortex line, you can do the same if you look at the phase information. And then you see when you apply this parallel field, then vortices twist, and at some point, the twist becomes big enough that they start to break, and then you will form these helical or periodic states. Okay, with this I will summarize. I want to read this just to show that our method basically helped to understand what is going on in these parallel field simulations, how re-entrance of superconductivity can be explained. And with this I will stop. And thank you for your attention.
Questions?
Yes, in the experiment of Philip-Diana, we see that the resistance goes to zero at a particular magnetic field. So what's the physical reason, or what determines this magnetic field?
I would say this is related to the thickness of the sample. So this is not a universal value, but this is just when the density of the vortex lines become large enough so that this helical motion becomes unstable or is suppressed again.
but it's determined by the thickness, then you should have a clear temperature dependence when of that position measurement field,
Yeah.
which they do not see there.
Well, I mean, the temperature range was really very small, so I think they do see a temperature dependence. I don't have this data, but this question I actually asked them, and they said they do see it.
What is the thickness?
100 nanometers, so this is about 16 zero temperature coherence frames.
To which extent is this helical motion of vortices the artifact of the periodic boundary conditions? And maybe you check actually what happens if you change the size of the
That's a good question. So this will always happen up to a certain thickness, but it always happens at the boundary. So it's energetically favorable at some point to break the vortex and go to the surface. And I don't think it's an artifact. But it's very stable.
Yeah, did you try to check whether you have some sort of Kibble-Suren mechanism here? Just generation of vortices just by quenching, because with your techniques you could really check this type of physics.
We didn't do this yet, but yeah, we will probably do that.
I want just to ask you, at these beautiful pictures where your vertex grows and then reach the surface, and then something happens. So you have change in boundary conditions for this. So what happens physically when we see in the picture the growth of this vertex when it touches the surface and then something jump?
Okay, I mean, this happens, so you increase the magnetic field.
Yes.
So you create a larger Lorentz force, basically, on the pieces of the vortices which are not parallel anymore to the current. And at some point they break, and then they, the ones which are close to the surface, they go to the surface because for energetically reasons this is more favorable. And then of course the Lorentz forces drag them, depending on their vorticity, to the left or right of the sample. And because you need to preserve somehow the vortex line, you always have vortex, anti-vortex going to these surfaces.
Last question.
molybdenum germanium is known as very low thinning material, so it's not obvious to me why we should have those defects in the first place, or at least why they should low.
I mean, you cannot avoid it.
Okay, sure. But on the other hand, you have, it's known that inelastic scattering time is finite, so you should have extra terms in your implement, let's say, Glatz formula, that you have a finite viscosity of the condensate, which is not in your simulations. And in principle, that should lead to some kind of phase slip in 3D, if you can imagine. Phenomena which could have actually very similar result and very similar consequences.
Yeah, I know what you're talking about, but
I think that should be much more favorable than some particular motion was across the entire sample.
I'm not sure. I mean, we studied this question actually, and we discussed with Gullit. And we are not really convinced that this is the mechanism which is responsible for this reentrance. Because also the simulations which were done to study this particular question cannot actually describe any reentrance. I mean, there's a tiny dip, but this is maybe 1%. And if you saw in the experiment, this is many orders of magnitude suppression of the resistance. So, I mean, we were not really convinced that this is the mechanism leading to this effect. But, yeah, it needs more discussions.
I think we're going to have to stop here, so let's thank the speaker.